Hello general chemistry students, this is the 5th video in week 12, and in this video we're going to be exploring the concept of LeChateliers principle. So by the end of this video you'll be able to not only calculate the reaction quotient but also predict the direction of a change. Right? You'll be able to apply LeChateliers principle to predict the response to a change. And by doing that, you're going to compare the reaction quotient and the equilibrium constant to determine the position of a reaction. All right, and so what you might have to do at the end of this video is also practice LeChateliers principle. All right, so the reaction quotient is the concentration of the ratio of products raised to the power, just like when we talked about the equilibrium expression, over the concentration of reactants raised to their power. That's the reaction quotient. So it's just like the equilibrium constant, except for the reaction quotient can be calculated throughout the progress of a reaction, while the equilibrium constant is for equilibrium concentrations. Right, so what we might want to do is if we have this reaction, we might want to calculate where is the reaction in the progress. Is it going towards equilibrium or is it going away from equilibrium? So we can calculate Q just like we did for the equilibrium constant. It's really the same thing, but these concentrations do not have to be at equilibrium. All right, so when we want to predict the direction of a change, what we want to do is we want to compare the reaction quotient to the equilibrium constant. So if Q is greater than K, the reaction is going to proceed in the reverse reaction. What that means then is the product is going to decrease while the reactants increase. So it's going to go in the reverse direction or to the left. If Q is less than K, then the reaction is going to proceed in the forward direction or to the right. So the concentration of products will increase and the concentration of reactants will decrease. When Q equals K, you are at equilibrium. Okay? That means the concentration of products and reactants will remain the same. So if you're looking at a reaction mixture that contains just reactants, Q is equal to 0. Right, so we saw that when we were looking at equilibria problems, and we wanted to know in which direction the reaction was going. So if a reaction is just products, then Q equals infinity, and the reaction will proceed in the reverse direction. All right, so let's look at Q, let's look at K, and let's look at the direction of reaction. All right, so if we have our concentrations of our reactants and our concentrations of our products, and here we have, in this case, oops, I need to find my pen. Here we have a situation where Q is less than K, so the reaction is going to proceed to the right. And here we have a situation where Q is greater than K, so the reaction is going to proceed to the left. And their goal is to get to that equilibrium constant. So you're either traveling towards that equilibrium constant, all right, towards the product, or you're reversing the reactant and traveling towards the reactants to get to that equilibrium constant. All right, so let's look at a reaction here. We have this reaction between iodine and chlorine, forms 2ICl. We're given a Kp. We want to find the direction the reaction will proceed. So we're given these pressures. We want to know, is this reaction going to proceed toward the product, or will this reaction proceed towards the reactant? Okay. If Q equals K, then you're at equilibrium. If Q is less than K, we're going to go forward toward reactants. And if Q is greater than K, we're going to go reverse towards the reactant. All right, so let's calculate these pressures and determine the QP. So we're really just inserting those those concentrations, or sorry, those pressures into the Kp expression. So we take our 0.355 and square it according to the stoichiometric coefficient, divide by then the reactants, 0.114 and 0.102. All right, and then we get our Qp, which is 10.8. Okay, so compare that to K, that's 81.9. All right, so what do we say? We see Q is not equal to K, so it's not at equilibrium. Here it looks like Q is less than K. All right, Q is less than K, so we'll say that the reaction is going to proceed to the right, or proceed to product, make more product. It's on its way. All right, and so for this reaction, we're given equilibrium constant. And for this reaction, we're measuring the concentrations and determining when the reaction is at equilibrium. If it's not at equilibrium, in which direction will the reaction proceed? So we have 3 experiments. In those experiments, we're measuring all these concentrations. Right? So we can set up that Q expression and determine, are we at equilibrium or are we not? So let's look at, so this is the Q expression. We have our CS2 times H2 to the 4th power divided by CH4 and then H2S to the 2nd power. So that's our Q expression, and all we're going to do here is we're going to insert those concentrations and determine where we're at in the reaction. Okay, so for experiment 1, we come up with 1.24, and 1.24 is less than Kc. Reaction's going to go forward toward the products. All right, let's look at experiment 2. In experiment 2, we come up with 5.86. Q is greater than K, which means we're going to then proceed to towards the reactants, or in the reverse direction. All right, let's look at experiment 3. We calculate here by adding in those adding in those concentrations, we get 3.59. All right, when Q is equal to K, we are at equilibrium. All right, so we have 3 examples here of comparing Q to K to determine where we are in the reaction progress. All right, so now let's dig in deep to this idea of LeChateliers principle. What we're going to do with LeChateliers principle is we're going to disturb an equilibrium. And an equilibrium is always going to respond, or the reaction will always respond in order to restore that equilibrium. Okay, so once a reaction is at equilibrium, the concentration of those reactants and products remain the same. However, we can change that, right? We can change the concentrations of those reactants, the concentrations of those products. What's going to happen is the reaction is going to respond to that disturbance in order to restore the equilibrium. Okay, so the new concentrations will be different, but the equilibrium constant will remain the same. Okay, so here enters LeChateliers principle. Okay, so LeChateliers principle is going to guide us in predicting how a change is going to affect the position of the equilibrium. All right, so really what LeChateliers principle is, it says that a system at equilibrium is disturbed. The position of the equilibrium will shift to minimize that disturbance. Okay, so it's going to want to shift so that it can bring itself back to equilibrium. That's LeChateliers principle. All right, so let's go back to our population analogy. So here we have country A and B, and remember they're free to go back and forth between country A and B. They've reached this equilibrium, and when they've reached this equilibrium, their populations remain constant. Okay, so now what we're going to do is we're going to disturb country B. We're going to disturb the population. All right, and so the result is that the people moving from country B into country A is going to be faster than people moving from country A to country B because we've added those people into country B. So the system is responding to minimize this disturbance. So this will continue until we've reached equilibrium. All right, so how do we disturb an equilibrium? One way we can do that is by adding or removing reactants. So if we have an equilibrium, it's been established, and a reactant is added, as long as that reactant is included in the equilibrium, all right, so we're not talking about solids and liquids here, then it's going to affect how we respond to that disturbance. Okay, so let's think about this. So we've added a reactant or we've removed a reactant. How is this going to affect the rate of the forward reaction? How is it going to affect the rate of the reverse reaction? Okay. How will it affect the value of K? Okay. All right, so adding a reactant initially is going to increase the rate in the forward direction, okay? Because we want to make more product because we want to restore that equilibrium. So the reaction is going to proceed to the right until that equilibrium is restored. All right, so now we're at the new equilibrium position, and you have more products than you did before, and then less of the non-added reactants than before. So at this new equilibrium position, the concentration of reactants and products will be such that the value of the equilibrium constant will be the same. All right, so imagine a situation where a reactant is removed. So as long as the, again, as long as that reactant is part of the equilibrium expression, this is going to affect the equilibrium. So how is this going to affect the rate of the forward? How will it affect the rate of the reverse? And how will this affect the value of K? Well, so hopefully by now we understand that the value of K will remain unchanged. But here we're removing a reactant. So the rate of the forward reaction will decrease and the rate of the reverse reaction will increase. So the reaction is going to proceed to the left or towards the reactants. All right, and so the reaction is going to proceed to the left until that equilibrium is restored. So at this new equilibrium position, you have less of the products than you had before, and more of the non-removed reactants than before. All right, so we've established the equilibrium. So the equilibrium constant remains the same. It's not changing. All right, so adding a reactant will decrease the amounts of the others and increase the amount of products until that equilibrium is restored. And so, because that is because the value of K must remain the same. So removing a product will increase the amount of products and decrease the amount of reactants. All right, so you can drive a reaction to completion by removing a product. This is in fact a strategy that biology uses in order to get reactions to go, is they can actively remove a product from that equilibrium so that it keeps driving that reaction forward. All right, so the equilibrium is going to shift from the side with the added chemicals towards the side with the removed chemicals. Again, establishing that equilibrium. All right, so let's look at this example. So we have one of our favorite reactions, N2O4 forms 2NO2. So if NO2 is added, some of it's going to make more N2O4. So in this situation, we're going to add NO2. So NO2 is the product. The equilibrium is disturbed. We're going to shift the reaction to the left so that we can make more reactant in order to establish that equilibrium again. All right, so initially we had Q equal to K here, so we're at an equilibrium. We added in the NO2. All right, so the NO2 increased, so the N2O4 that we added in is going to decrease over time, and eventually we get to the same equilibrium, okay? So that difference between the reactants and products is going to be the same no matter what has happened, because we're going to reestablish that equilibrium. So we've added the N2O4. Some of it's obviously going to go away over time as it reacts, and then we're going to form more of the NO2. Okay, so how does this work for a gas? So remember, we're going to use gases in our equilibrium expressions as partial pressures. So so if we're adding in more gas reactant, increasing the partial pressure, that equilibrium is going to shift to the right towards the product. Okay, so think of it as adding a reactant so that we now shift to the product. All right, so increasing the partial pressure increases its concentration. So we can think of partial pressures really just being a concentration. Another thing to think about is, what if we add in something that's not part of the equilibrium expression, like an inert gas? That's not going to do anything to the reaction. All right, well, what does volume do? All right, so decreasing the volume increases the concentration, which increases their partial pressure, but it does nothing to change the concentration. So just changing the volume is not going to change the equilibrium. But if their partial pressures increase, then the total pressure in the container will increase. And so what's going to happen is that, according to LeChateliers' principle, the equilibrium is going to shift to remove that pressure. All right, and so we're going to shift to reduce the number of gas molecules if we increase the pressure. All right, so when the volume decreases, the equilibrium is going to shift to the side with the fewer gas molecules. And you can also think about it, well, what if you have a situation where you have the same number of gas molecules on either side? Well, then nothing's going to happen. All right, so we're going to change the volume. So after the equilibrium is established, the container of the volume is decreased. How is it going to affect the concentrations of solids and liquids, solutions, and gases? Well, it's not going to affect the concentration. We already said that. How will it affect the total pressure? Well, it's going to It's going to increase the pressure. Well, how is it going to affect the value of K? Well, hopefully by now we've learned that the value of K is not going to change. All right, so decreasing the volume will increase the total pressure. We know that by Boyle's law. And if the total pressure increases, the partial pressures of all the gases must increase. And if the total pressure increases, the position of the equilibrium will shift to decrease the pressure by removing gas molecules. Or, said another way, it'll shift to the side with fewer gas molecules. Okay? Again, if they're the same on either side, nothing can happen. All right, so let's look at an example when we're going to affect a volume change. So here we have our reactants, and we have 4 moles of each, and we have our product, we have 2 moles. we're going to increase the pressure because we're decreasing the volume. All right, so there are more gas molecules on the reactant side. So we have 4 moles of gas. Than we do on the right-hand side, we have 2 moles of gas. So when the pressure is increased, the position of the equilibrium will shift to the fewer gas molecules. So we're going to go to the right, just like the arrow says. So we're going to shift the equilibrium towards the product because there we only have 2 moles of gas. All right, another situation is where, okay, so now we're going to decrease the pressure by adding more volume. All right, and in this case, the pressure is decreased because we have more volume. And therefore we're going to shift to the greater number of molecules. So here we're going to shift towards the reactants, all right, because we have decreased the pressure. All right, so how does temperature play a role in the equilibrium position? So it depends on if the reaction is exothermic or if the reaction is endothermic. Because exothermic reactions release energy, so we can think of heat in an exothermic reaction as a product, and in an endothermic reaction, it absorbs heat, so we can think of the heat as a reactant. So we're going to write heat as a product in an exothermic reaction and heat as a reactant in an endothermic process. All right, so look at this. So we have an exothermic reaction, heat is a product. We're going to increase the temperature. So we're adding heat, right? We're adding a product. What's going to happen? According to LeChateliers, the equilibrium is going to shift away from the heat. So it's going to shift towards the reactant. So adding heat to an exothermic reaction will decrease the concentration of products. Right? Decrease the concentration of products. Adding heat to an exothermic reaction will decrease the value of K because remember, heat is not a concentration. So you are actually changing the value of K here. What do you think will happen if you decrease the temperature? Decrease the temperature, you're going to shift to the right. All right, so let's use the endothermic reaction. Here, heat is a reactant, okay? So if we increase the temperature, all right, we're increasing the temperature, we're going to send that reaction to the right or towards the products. So according to LeChatelier's principle, we're going to shift away from the heat and we're going to add more products to this reaction. All right, by adding heat to an endothermic reaction, you are increasing the value of K. Remember, heat is not part of the K expression, so you are changing the value of K when you add heat or decrease heat. All right, by decreasing the temperature, you will increase reactants, so it's opposite. All right, so the effect of temperature changes on an equilibrium. So remember, it depends on if the reaction is endothermic or exothermic. So in this case, this reaction is endothermic because heat is a reactant. Okay, and so what that means then, in an endothermic process, a lower temperature is going to favor reactants, while a higher temperature is going to favor products. All right, what about a catalyst? So the catalyst is a bit different because a catalyst provides an alternative mechanism. And so catalysts can work in the both forward and reverse reactions. And they affect the rate forward and reverse reactions by the same factor. So therefore, adding a catalyst does not change the equilibrium. All right, so even though we're changing the mechanism, it's not going to change the position of the equilibrium. All right, so let's look at all these examples. So we're given this reaction. It's in its gas phase, and we have 3 molecules in the reactant and 2 molecules in the product. And this reaction is exothermic, okay? Exothermic, a negative enthalpy. So how will each of these affect the equilibrium of each gas once equilibrium is restored? Okay, so the first thing is we're going to add more O2 to the container. So effectively adding more reactant. Condensing and removing SO3, we are removing SO3, so we're removing a product, so we're shifting towards the right. All right, so for O2, we're shifting towards the right. By removing a product, we're shifting towards the right. If we compress the gas, all right, we're going to, so a higher pressure, it's going to move towards the, one with the lower number of gas molecules, and that's the product. So we're going to shift towards the right. If we cool the container, all right, so let's think about this. It's exothermic, so heat is a product. So we're taking away a product. It's going to shift towards the product. Doubling the volume, so we're decreasing the pressure. It's going to respond towards the side with more gas molecules. So we're going to shift to the left. Adding helium to the container. Notice helium's not part of our reaction, so nothing's going to happen. All right, that's adding an inert gas to this reaction. Nothing's going to happen. Adding a catalyst. All right, we just said it doesn't change the K. The catalyst isn't going to affect those relative concentrations, so no effect. All right, so that's the end of our 5th video on LeChateliers principle. Thank you.